You mean I can have more powers than just 2? Does that make them superpowers? Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. Today we are taking a look at polynomials, which are the big ol' family of functions that includes quadratics and linear functions, and functions to the third power, and to the fourth power, and to the millionth power. And polynomials are the family of functions that have various terms of differing powers of x in them. The highest power of x in the polynomial is called the degree of the polynomial, and it really sets the behavior of the whole function. The general form of a polynomial is this. Hidden within all this notation is the fact that each term within the polynomial is defined by a power of x, x to the n power, x to the n minus 1 power, x all the way down to the x to the first power, x to the 0th power, and a coefficient, a sub n minus 1, a sub n minus 2, all the way down to a sub 1 and a sub 0, where a sub 0 is our constant term. A sub n is something called our leading coefficient. This notation also reflects the standard form for polynomials. We saw this earlier with quadratics with ax squared plus bx plus c, and with linear functions, ax plus b. But now we have functions that could be ax to the fourth plus bx cubed plus cx squared plus dx plus e, or ax to the seventh plus bx to the sixth plus cx to the fifth plus bx to the fourth plus bx, etc. All polynomials have some basic properties, which we'll go over now. For the x-intercepts, any polynomial can have as many x-intercepts as its degree. So a degree 4 polynomial can have as many as 4 x-intercepts. It can, however, have less than that many x-intercepts. If the degree of the polynomial is odd, it will always have at least 1 x-intercept. In the complex world, a polynomial will always have as many roots as its degree. But in the real number system, the number of roots can be less than or equal to the degree of the function. Let's look at this function as an example. F of x is equal to x cubed minus 3x plus 2. I know, because I made it this way, that this function factors into x plus 2 times x minus 1 squared. So what are the zeros of this function? I know this function is 0 at x is equal to negative 2 and x is equal to 1. That second root, 1, repeats. I know this because the term x minus 1 is squared in the function. Another name for a root that repeats is that it is degenerate. When I have a root of even degeneracy, for instance, if that was x minus 1 squared, or x minus 1 to the fourth, or x minus 1 to the sixth, that means that the function is going to bounce off the x-axis at that point. Unique roots, like this one, x plus 2, mean that the function crosses the x-axis at that point. The same thing will happen if you have a repeating root of odd degeneracy. Finally, if any of my roots are complex, that reduces the number of times that the function touches the x-axis by 1 for each complex root. Now, complex roots always come in pairs, so therefore, if I have 1 complex root, I have 2, and I'm always going to be missing 2 roots from my total times it touches the x-axis. For the end behavior of polynomials, it really depends on what the leading coefficient is, as well as the highest degree. To look at end behavior, we're gonna split these functions into even polynomials and odd polynomials. Even polynomials have the same end behavior as quadratics do, because quadratics are an even polynomial. For instance, for x approaches negative infinity and for x approaches positive infinity, if a is positive, then the function always approaches positive infinity. If a is negative, then the function approaches negative infinity as its end behavior. Odd polynomials follow the same end behavior as linear functions because linear functions are odd polynomials. If x approaches negative infinity and a is positive, the function approaches negative infinity. X approaches positive infinity, y approaches positive infinity. If a is negative, as x approaches negative infinity, the function approaches positive infinity, and as x approaches positive infinity, the function approaches negative infinity. The pattern is that for even polynomials, the function approaches the same value of infinity at either end of the x spectrum. For odd polynomials, polynomials, the graph goes from one corner to the opposite corner as x approaches either side of the infinity spectrum. For domain and range, we're again going to separate these into odd polynomials and even polynomials. Odd polynomials are the easy ones. The domain and range of odd polynomials is just all real numbers. Even polynomials are a little bit different. The domain of even polynomials is all real numbers still, but the range depends on the biggest extrema of the function as well as that leading coefficient a sub n. Unfortunately, there's no good algorithmic way of saying that the range of a polynomial is from negative infinity to this number or this number to positive infinity. Instead, we have to take it on a case-by-case basis by finding out what are the extrema, the maximum and minimums within the function, and determining the range based on that data. In the next video, we'll be applying these ideas, but in the meantime, why don't you try out this problem yourself? What are the zeros of this polynomial function? Thanks so much for watching, and I'll see you in the solution.